at optimization and some of the other really cool tools that are in Xcode, Xcode 3 and 4. Next week, we're going to start the bonus lectures. There's a poll up on Piazza for your vote for what bonus lectures you would like to see. We want to custom tailor those to what your needs are, so please go there and vote ASAP. Okay, so there are two projects that are associated with this. I'm going to demo these along with the instrument readouts. If you're having trouble seeing, I suggest coming up here. This stuff is actually really important. This is another tool in your developer bag that is a necessity if you're writing a well-polished and good application. This will help you not only find like just raw speed numbers and performance bottlenecks, but it'll also help you find memory over allocations and not being released or being released too late. It'll help you with multi-threaded problems. There's a whole number of things that this can do. Just a note, I'm going to be demoing the Xcode 4 version of this. The Xcode 3 version also has an application called Instruments that you use almost in an identical fashion. The Xcode 4 version has got some updated features. The Xcode 3 version is very competent, though, on its own. The only difference, actually it's kind of a big difference, is a very tight integration with Xcode 4 and instrumentation tool. It's really simple to launch back and forth between the two. With Xcode 3, it's basically a separate application. It's a little bit more work, but it's really not that big of a deal. If you're struggling with it during the lab, just let me know and I'll help you out. There's a bunch of documentation too about Xcode 3 instruments. So this project, there's two projects, one called Time Me and one called Slow and Buggy. This one called Time Me has got, it's just a raw C program that has it has three main kind of characteristics to it. It's got or three main functions to test these concepts out with. The first one is just two functions called Time Me that are basically memory allocators. I'll show you those in a second. There's factorial, written iteratively, recursively, and with tail recursion. And there's a Fibonacci, written with recursion memoization and iterative memoization. So the first one that I'll show you are the memory allocation functions. It started out as Time Me. I should rename them. But essentially all it is two functions that just allocate a bunch of memory and then free it, right? And sorry, let me roll that back again. It's two functions that allocate memory. The first function allocates the memory of increasing size. It touches the memory. It just touches memory location 0 to make sure that it doesn't get optimized away, that these calls don't get optimized away, and then frees it. That's all it does. The second function is identical to the first. The only thing is it does twice as many memory allocations. And you can see that the size of the memory allocation is in accordance to the loop variable. So if we run this, there's really nothing to see. There's really no output that you'll see here. But the real kind of magic goes on when you peek underneath the hood. In Xcode 4, under the product menu, you do profile. When you call up the profile, the instruments application will launch. Actually, let me move it over here to another window. It's okay. The profiling application will launch. On the left-hand side are the instruments that you can use to profile your application with. They subcategorize them with in memory-related, like leaks and zombies, and just tracking raw object allocations and activity and garbage collection. There's CPU, which does just the basic time profiling along with multi-core, multi-threaded profiling, system traces to trace system calls and the amount of time that system calls are taking. There's also file behavior where you can check file reads and writes and accesses. And then there's behavior. Here's one that's really, really convenient called sudden termination, and I'll show you that in a second, which will record a whole bunch of information leading up to your app, especially your iOS app, suddenly quitting and being able to figure out exactly what went wrong. And then there's Cocoa. There's things about Cocoa layout. The UI recorder is in here, which generates the JavaScript to do automated UI testing. That's kind of way beyond the scope of this, so I'll leave that to you to go into. Then there's also some user-specified tools that you can create. That's also outside of this scope, and I'll let you explore those too. So with leaks, let's see. Actually, what we want to do is we're going to do a time profiling of this. And you'll see here are the main components of the window. You have your toolbar up top here that has a bunch of additional functionality. You've got the instrument on the left-hand side, which is the current instrument that's running running your app under. There's on the left-hand side are some tools that you can use to help change the visualization of the output to make it clearer to you. This is the timeline here. Something that is really convenient is under view you can do snap track to fit, which will expand that timeline to be exactly when your app launched and exactly when it quit. And then down here is the meat of the data, meat of the output. This is basically all of the function calls that were made, system calls as well as your own calls. This is the amount of time that they took on the left-hand side. And on the right-hand side are all the symbols. And you'll notice that most of these symbols, in this case, almost all the symbols are all system symbols. This is when you would use one of the options on the left-hand side. You can hide the system libraries just so you can see your own code. Yes.
So I know for Java, when you touch a profile, right, it's super slow. Is it the same thing for Objective-C?
No, it does run on a thread, so it does use some core time, but it's really, really lightweight. It's a very lightweight probe. It uses like some of the lowest level dtrace stuff that's built into the kernel, so it has a very low impact. So we'll see. So we see our two functions here, time me 1 and time me 2. Here you can see the percent of the time that was taken. If you look at the code, what would you expect? Time me 1 in relation to time me 2. Two's going to take longer. How much longer? Well, here's a clue. It's doing twice as many memory allocations. The code's identical. It's doing twice as many memory allocations, so you would probably anticipate that time me 2 would take twice as long as time me 1. If you look at the breakdown of the running time, you'll see that time me 2 takes 83% of overall running time, and time me 1 takes 14%. So what we can do is we can take a look and we can drill down and see the call stack of each one of these routines. You'll notice that it's inverted, where you're seeing the major time. The functions that took the most amount of time will be listed up at the top, and then the calling stack underneath that. That's toggleable with this checkbox on the left, invert call tree, and that will show you things in probably something that you might be more accustomed to, which is see the top level and then see all of the time profiling breakdown on the way down the stack. So you'll notice that start is the first thing that's called. It's actually called outside of your program. It's basically a kernel call. And then here's our main, and then here are the two routines. If you double click at any time, it opens up a copy of the source code and shows you percentage-wise exactly how much time each one of those routines took. If you open up on the right-hand side here, if you open up the right-hand view, you can see the call stack on the way down here. You'll see an extended detail for certain things. You'll also see the call stack and the times taken on the right-hand side, and then the source file and the line number that it came from. It's one really cool thing. I'm not sure Xcode 3, the Xcode 3 version of Instruments does this, but this version, everything's all hot linked. So we can click on our functions and go directly to them and see the time that they took. You'll see memory time me1, 66% of the time was spent in the allocation and 33% of the time was spent during free. If we go back and look at time me2, you'll see that 8% of the time was spent in the allocation and 88% of the time was spent in free. This is all, by the way, hot linked too, so if you really feel like diving into the assembly, you can take a look at it and see exactly how much each one of the calls took. And you can dive into these too. If you forget what some of these assembly language calls are, well, it's got, we can open up the ISA reference guide and take a look at every single one of the calls. It's very full featured, as you can imagine. This is just going to be a short overview of everything just to kind of get your feet wet, because you're going to be able to play around with a lot of this stuff during the lab today. So we can look and we can see that time me2 took way more than twice as long as time me1, so something else must be going on. So one thing that we're doing is we're doing a bunch of memory allocation. If you open up the library here, it's one of the tools on the toolbar. It's also in the window menu. These are all of your instruments here on the right-hand side. These are all the built-in ones, and then ones you can create your own will be in here as well. So what might be happening here is there's probably something that's going on with the memory allocation. So what we'll do is let's look at the VM tracker. So we just drag the tool over on the left-hand side, and when we can see, and this is important for Xcode 3, you can see the target of the current application that you're gonna record the trace on. In Xcode 3, you might have to do this manually. It's been a little while since I've used it. In Xcode 4, once you do analyze from Xcode, you flip instantly right back here. So when you click record, it'll start another run. You'll see it's over really, really fast. We can expand the timeline out here. This tool shows the resident memory size and the dirty memory size as a function of two stacked bars. That's way more information than you might need right now, but the documentation is really complete on this. We can take a look here and we can see that we are requesting about 116 megabytes of virtual memory in our app. So as you can probably guess, and I'm not going to continue on with this. I kind of dove into this and it took a little bit longer than I was expecting to try to explain. But essentially, we're hitting the VM wall here. We're hitting a virtual memory wall where we're starting to have to allocate a lot of memory from virtual memory, and there's running into a lot of swaps. And interestingly enough, the free call can take an inordinate amount of time when it's trying to deallocate and reswap pages around to have faster memory access. If you go, clicking on the instruments will change the detail that you see on the lower right. If you're sitting here if you open up your code and you see something that you want to modify in Xcode, there's an Xcode button, mini toolbar up here, which will take you to Xcode at the place that right where it'll open up the code right where you have the window open here on the bottom right. There's also other output that you can get in the bottom right. There's a list of all the samples that were taken, the time samples that were taken, what zone, the memory zone that it was in, the depth, the CPU core that it was on, and a timestamp. Very detailed information. There's also a console that will show your program's output, like if you're logging things, so you can check here. So that's the first one. The next one that we're going to time is we're going to check. We're going to do a factorial, and we're going to do it iteratively, which is right here. We'll just do a very simple iterative factorial. We'll do a recursive factorial, and we'll do it by adding a tail multiply on the right. So this This isn't a version. This isn't tail recursion, and we have a version that is tail recursion, where it's just calling. It's just returning exactly what's been called, and that'll become important in a moment. So I've got the optimizations turned off right now. If I run this, what do you suppose the time breakdown is going to look like? Let's take a look. Yes. So when we look at, we've got timing as this is our main function. We've got the recursive factorial, which calls the recursive factorial, which calls the recursive factorial, which calls recursive factorial a lot of times. Tail recursion, if we look at that, does the same exact thing. You can see exactly how much time each one of these recursive calls took. You can also, with an option on the left-hand side, flatten recursion, which will scoop up all the times and turn it into one big, essentially one big call. So if you look, 66% of the running time was in recursion, was in the recursive non-tail recursive version, and 33% of the time in the tail recursive version. This is with optimizations turned off too. So there's probably some tail recursion optimization that's going on even with the optimizations turned completely off. And it may just have to do with the way that the stacks are built. If you're really super curious, you can of course dive in if you want to and find out exactly what's causing the most amount of time. But you can see here that when we look at, where's the close on this? And there's the instructions if you want them. Most of the time is being spent with stack manipulation here that's happening before it's even the call's even being made or your code's even starting. If we look back here again, we can see that what was I looking for here? We can see that factorial iterative doesn't even show up on here, which, yay, great. Our iterative factorial is really super fast, but that might not be the level of detail that you need. Each one of these instruments has got an information panel associated with it. Right now, the sampling rate is 1 millisecond. It can go all the way down to 40 nanoseconds, so we'll use that, and we'll run it again. All right, so 96% of our time was spent in our call. We look inside here. We'll see that it's more detailed, and it's much more detailed in its breakdown. But it's still, the iterative version is still too fast for this to pick up on. This is something that that you'll notice for really small functions. It's actually kind of a benefit to be able to have sampling that doesn't pull so much data in that it becomes overwhelming and useless. I can show you how to tease that out if it comes down to it. But for right now, I'm gonna kind of leave that as an exercise for the user to do. So let's go back here and switch the optimizer on. This is one of the things, incidentally, that is in the lab today, is to check the different versions between an optimized and unoptimized version of your code. Let's do fastest and smallest. We'll start timing it. And you'll see that our main program here takes almost no time. The iterative version of the factorial took 16% of the time, and the recursive version, almost none. That I'll also leave that as an exercise to the reader. That's also a the tail optimized version. You can actually force this to show you that the tail optimized version with the little finagling, you can show that the tail optimized version works much better than the recursive version. And to understand that, that Wikipedia's got some really good write-ups on tail recursion. Another really cool thing here is as you make runs and as you make updates and changes to your program, and I'll show you this in more detail with the second project, but it saves your runs across each one. It saves the data across each one of your runs. So you can see where time, in this case for this instrument, you can see where time is being taken in accordance to overall time. You can see our unoptimized version took this amount of time, the full windowed width, whereas our latest run took much less time overall. So let me change, I'll leave that for right now. Let me switch over to the other project. So you're thinking, well, that sounds like regular GProf, that sounds like regular performance profiling stuff. How does this kind of translate to what you're doing or what you may be doing? And so what I've built here is a really simple iOS app that basically all it does is present you with a list of choices. It's got a text field for numerical entry, a list of choices for a bunch of different types of sorts that you want to do, and then a couple extra options down at the bottom that I'll tell you about in a second. Who knows what BOGO sort is? Random, yeah, random, shuffle randomly and test it. Is it sorted? No. Shuffle randomly, tested, sorted? No. Shuffle randomly until it happens to. It's going to be big when quantum computers become commercial. Trust me. So it gives you the total amount of time that it takes, and I'm not going to do that. Total amount of time that it takes and the throughput. Those are just text fields. So this is sorting, and other algorithms like this are ripe for being profiled. This is testing your algorithms, whether they're really complicated or really simple. This is the tool that you use to do that, to check to make sure that you've got an efficient solution. This is obviously not an efficient solution. Let's stop this and run this again. So we'll do a 1,000 element bubble sort. What's that? 6/1000ths of a second. Actually, let's make this 10,000. Try a bubble sort. So that takes 0.4 seconds. A selection sort takes 0.13. Insertion 0.08. Quick sort 0.002. So this gives you, this is a project that you can use to test different sorting algorithms and test them with profiling. There's also hog-mem sort, which is basically just, actually here I can show you what it looks like. All it does is allocate a whole bunch of integers, allocate a memories with a whole bunch of integers, and then touches it to make sure that it doesn't get optimized away. So if let's show the interesting case here. Let's run this under the profiler. Actually, here, let me close this document out so it's not confusing. Let's run this under the profiler. Let's time it. So we're going to go 10,000 element bubble sort. You can see it collecting the data here in real time on the lower right. You can quit out of this, or you can just click the stop button here. We can see that bubble sort was 85% of the time. We can take a look and see that we can see exactly where time was taken, and in this case, most of the time was spent in this for loop, which includes initialization and conditional. Again, you can take a look at the source and the call stack. Let's see, where is that? You can see the call stack here. You can see everything from where our application started to UI applications main, all the way up through the event clicks, finding the right view to send it to, the view to send it to, and then ultimately to our bubble sort. Again, you can hide all of the system libraries if you like, so you can just focus on your code. If you take a look at, let's run this again. We'll compare the sorts now. We'll do a bubble sort. Oh, I shouldn't have done 100,000 items. Let's try that again. Do 10,000 items, do a bubble sort, selection sort, insertion sort, quick sort, and we'll do a hog mem sort just for the hell of it. Quit out. So because we've got the call tree inverted, we're going to see the highest, time, the longest time spent is going to show up here. You can invert this so you can see how much time it was taken as a percentage of overall time. We can, with the option on the left, invert the call tree so that we can see it as maybe more useful for you to be able to see the call stack from a top-down view. So you can see in this case, this was logged. These were logged after and including when the button was pressed. So if you take the button out of the equation, you can see that it just took a tiny fraction of the time slice, and you can see relatively you can see exactly how long each one of these took. Then you can just as before drill in and see exactly which portions of your routines were taking the longest. Since hogmem sort actually has some memory allocation, we can take a look at. Let's take a look at the VM. Actually, you know what? Yeah, let's do the VM tracker. Let's also look for leaks too while we're at it. Start it. We'll do 1,000 hogmem and quit. So here you can see all of the memory allocations that were made. You can see exactly the sizes that were made. You can turn on, if you're doing leak detection, you can gather the leaked memory contents, which means it'll hold on to buffers even after your app has quit. So you can take a look at the contents of a leaked buffer if you can't figure out where a leak might be coming from. One thing you'll notice here too, the default is set pretty high for it has to take snapshots of memory to determine when you've got a leak and when you don't. Right now the snapshot is set pretty high at 10 seconds. So you'll see that in our leak graph here, you'll see that that it didn't discover any leaks. What we'll do is we're going to turn this down to make the snapshot happen more often and try running it again. So we do 1,000, hog the memory, and quit. This time we had a lot of leaks, and you can see exactly the size of the leaked objects and the library that was responsible for it. Again, you can turn off where is it? There's a way to turn off let's see if I can. There is a way, I'm not going to try and find it right now. There is a way to shut off all of the system libraries so you can see exactly which of your routines was at fault. You can see when you click on any of the memory allocation or any of the memory leaks on the left-hand side, you'll see exactly where it came from in the call stack at that point. So the symbols on the left-hand side show you what's a system library call, like malloc, what's Cocoa application frameworks, like UI application send action to from object. Then the little person icon here is user code. That's code that you've written. That's part of your application. You can see if you double click, you can see exactly where the leaks are coming from too. You can see here that we allocate various multiple sizes of memory, but we never free it. And that's where, and I've got this commented out. So you can see that's where 100% of these leaks were coming from. So what we'll do is we'll uncomment this. Let me switch back to Xcode. Uncomment this and launch it again. Quit. So much better. Compare our two runs. Compare our first run to our second run, which had thousands of leaks. However, we still have a leak somewhere. Still a 4K leak that's happening somewhere. So what we'll do is we'll gather the contents of the leak and run it again. Oh, come on, dog. You can do it. Let's see if I can get it with these other. There we go. So every time I press a sort button, I'm getting a leak. This time I pressed tried two of the different sorts, and I got 2 different leaks. You can see on the right-hand side where it's coming from. You can see the contents of the memory, the leaked memory on the right-hand side. If you want to look at it, you can look at it as string data and things like that. So it might give you a better clue as to where it's coming from if you don't see the frame in the library that's responsible for it. But if we take a look at the library, we can see that there's a little utility routine that I wrote called generate random integers that just allocates memory for a certain size integer, and that's what we put in that text field, and then fill it full of random integers and return it. But nobody's responsible for freeing that. So here's a perfect example of why auto-release exists. Right now, I can generate these random numbers by allocating memory and returning it, but who's responsible for it now? I could have an end generate or clean up generated random integers function if I wanted to and pass that pointer back in and free that, or I can say that whoever's using this is responsible for freeing it. There's no comment here, so there's no way to tell. The only way that you would see this is if you ran a leak report like that. If we go back to the controller here, and we can see where we're allocating the integers and then sorting them and then updating the labels with the amount of time that it took. We're not freeing them. So we free them here, run it again. BOGO sort, 10, bubble sort, selection sort, insertion sort, quit. No leaks. So the last piece of this is down here on the bottom right. There's a button called spawner. Basically, what it does is it spawns a thread, a background thread, to do a BOGO sort in the background while your app is running. We can give it, say, 20 integers and have it start running away. You'll see that your app is still active. I mean, it's running on a thread, but things are running more slowly than usual. If you spawn a couple of threads, things are gonna start to really bog down. It can be really difficult to figure out in a multi-threaded application exactly what is taking time. And if you start using things like Grand Central Dispatch, which you haven't talked about that yet, right? If we talk about Grand Central Dispatch, which is a really clean way to do a lot of multi-processing work, it's really important to be able to understand where time is being taken in your application, what may be causing slowdowns. This goes for either OS X apps or iOS apps. In fact, if your app becomes unresponsive enough, the iOS will just kill it, and it'll drop back to the home screen. Understanding why that's happening is really, really important. So what we can do is we can go to our time profiler and we can take a look, and we see that 95% of our time was being spent when we clicked that spawn button, and that is calling BOGO sort. We can take a look, and you can drill down in and see exactly what was taking the most time. But the really important thing is to be able to see this spawn message is actually being launched as a thread. When I press the button, I launch a new thread with the spawn message, which spawns this thing in the background, but then lets the main application keep running. So understanding where this time is disappearing, and also if you've got memory leaks in there, is really, really key. It's really, really important. And the instruments makes it really easy to figure out, and the Xcode debugger make it really easy to see thread usage and how much time is being taken on a specific thread and how many or resources a specific thread is using. There's even a threading library instrument in the library. There's actually a number of them. There's thread states, so we can look at thread states. We can also use this sampler that just cuts across, cuts time samples across at a specific interval that lets you be able to see exactly which threads are forefront and which threads are running in the background and which ones are, and how much time it's taking to process swap them. So we'll launch another one here. We'll spawn a background, and we'll do a bubble sort of 10,000 integers. We can stop and we can take a look, and we can see with thread states, we can see exactly which threads were on which CPU, how much time they took. You can see via a graph how much time each one of the threads was swapped in and swapped out. Really handy, really, really powerful. I think that's it. Is there anything else that I wanted to show in there? No. So, lab today is play with instruments. Try it out. Bang around with your code. Bang around with this code. Use try the Sudoku code and figure out where the solver is spending most of its time. Figure out if you've got leaks in your app. If you've gone so far as to multi-threading your apps. Figure out if you're utilizing thread time efficiently and effectively. You'd be surprised at how many people, even nowadays, with just a misplaced thread join, can kill the performance of their application. If you've got an app, say a web browser is a great example where you want to say spawn of multiple threads and then to go to pull resources off of different servers and then put them all together and come back again. And you've got another thread, your main thread is handling your user interface. You'd be surprised at having a bad thread join in there at the wrong place or the equivalent can throw off the overall responsiveness time of your application. So this is definitely a tool that you want to get comfortable with using because it not only tells you, it not only gives you, you've seen performance feedback, but also gives you feedback about your memory allocation. It also does garbage collecting. Hint, hint, if you think that automatic reference counting solves all of your problems, magically solves all of your memory problems, you might be surprised once you start building a larger application how much memory management still can become an issue. And algorithmically solving that rather than just turning on automatic reference counting and assuming that it gets solved for you is the way that you are going to need to go when you are a big grown-up developer. All right, questions. So you'll be experimenting with this stuff during the lab, and we'll all be wandering around answering questions that you might have about it. If there are Xcode 3 specific things, I'll probably post them up on here just so I don't have to answer it a number of times. They're very similar to each other. Some of the UI may be a little bit different, but the documentation should still be correct for instruments on Xcode 3. Questions? Nope.